Good morning to you all. I hope you're all enjoying the presentations that have been put together and based on the work carried out using the ASPI software. I would first like to acknowledge my learned co-authors for this presentation as you see them listed on this slide. Dr. Ritesh Kumar Sharma, Dr. Kurt Marfut, and Dr. Heather Beetle. Mm, All right. When we talk about the improvement in resolution of the input seismic data, we know it is a desirable goal to meet the objectives for exploration and development. And such an improvement can take place with the use of a procedure or a technique which enhances the dominant frequency in the data or widens the bandwidth of the input seismic data. While processing, significant efforts are made um, to enhance the frequency in whatever way. But the shortcoming of the processes, such as multi-window statistical deconvolution that is applied, inverse Q filtering that is used, as well as the time-varying spectral whitening sometimes that is used, and it proves to be ineffective when the reservoir intervals to be characterized are thin. So as a result, some advanced methods they have been utilized for spectral, or they have been developed for spectral balancing as well as extension of the seismic data. Now uh, the type of challenges that we deal with in reservoir characterization these days includes sharper definition of the reflection events and resolution. If not anything sophisticated, we can begin with spectral whitening of the data, right? So spectral balancing essentially entails the flattening of the frequency spectrum of the seismic data, and in the process results in better resolution and thus the sharper definition of the reflection events that we are to interpret. In this presentation, we will begin with showcasing some applications of a method that is available in the ASPI software. And so that is what we'll be highlighting. Now, in this method, the data are first decomposed into time frequency spectral components. And the power of the spectral magnitude is computed as given by this expression. And then once that is done, the spectral magnitude is averaged over um, over all the traces in a lateral sense as well as in the time window of interest. And that is given by the expression that you see here, that is P average. After this, the peak of the average power spectrum is also computed, which is given by this expression. And once that is done, then both the average spectral magnitude and the peak of the average power spectrum, they are used to design a single time varying spectral balancing operator, which is then applied to all the traces in the data. So this slide shows vertical slices through seismic amplitude volume. On the top before that is the essentially the input seismic data, and below is the equivalent section from the data after spectral balancing. The amplitude spectra are also shown in the inset. Now, as you can see, there is higher frequency content on the lower image, as seen as compared with the image above. Especially in the highlighted zones that I have shown here, you can make that out much better than at other places. Now, encouraged with the high frequency content of the data, we run energy ratio coherence on the input data as well as the spectrally balanced versions of the data, and those are the two images that you see on this slide. Uh, we see better definition of the north, northwest, south, southeast orientation faults that you see here, that they are much better defined as compared with what you see on the left. And then similarly, the east-west orientations, almost east-west orientations on the spectrally balanced version, they are defined much better. A similar exercise was carried out on another data set from the Hoop fault complex in the Barents Sea. And spectral balancing was carried out on the input data, which you see on the top, and the equivalent section. And of course, this was carried out after structure-oriented filtering was run on the input seismic data. And a similar exercise was done for the spectrally balanced data. So you can notice the crisp definition of the faults. First of all, we are looking at time slices through the two volumes at 10, 20 milliseconds. It will give you an idea of the time at which we are showing them. The crisp definition of the faults and channels that you see in these two images, you can make that out. It is defined much better on the image below. The frequency spectra or of the two for the two types of data are also shown on the right hand side. A much better flatter spectrum that you see here. And yet another data set I show from northern Alberta, Canada, and here is the input data that you see as a section from the input seismic data, and the equivalent section that I now first of all, before I go to the next one, you see the two impedance logs that are shown overlaid on it, and a similar version of the section that I show, or the spectrum that you see that is also given on the in the inset. And this is the data after spectral balancing. And notice here input and output, input and output, and the flatter spectrum that you see there. So now, when we talk of spectral balancing of the seismic data, we should also be concerned about generating spurious reflection events as well as the distortion of the seismic amplitudes, which may happen with the application of the algorithm used in the method that is used for the purpose. And one way of checking this is to pick up the angle stacks that are generated for use in simultaneous impedance inversion, and we can analyze their amplitudes as a function of the angle of incidence. That is before and after spectral balancing. Notice on this slide, the angle stack traces are shown on the left. These are from the input data, and the equivalent traces at a given point from the three angle stacks after spectral balancing, they are shown here. And for the reflection events that are marked here by the red bar before spectral balancing and after spectral balancing with the blue bar, if you notice this, these are um, the amplitude values as a function of the angle of incidence. Barring a small change in the amplitude of the events after spectral balancing, the relative amplitude variation with angle is very, very similar. And that is what we are interested in, not to distort the amplitudes as a function of offset or angle in any way. We take this exercise forward to running simultaneous impedance inversion, and here we are showing a comparison of the P impedance section generated on the seismic data before and after spectral balancing, which is shown below. And on the two displays, we see the strip logs as well as the curves for the impedance logs overlaid. Now, as is indicated by these two yellow block arrows, there is mismatch between the log and the inverted impedance on the upper section, while a much better match is seen on the lower section. Also, the intervals to the right, which I have indicated with the braces, the blue one corresponding to this zone, and that is equivalent to this zone. So notice in this one, the frequency content looks better as compared with what you see on the top. Similarly, what you see for corresponding to the purple braces, this interval, it shows much better definition of the reflection events here. So then in the pre-stack simultaneous impedance inversion, we use multiple partial offset or angle substacks, and they are inverted simultaneously. So for each angle stack, a unique wavelet is first estimated from seismic data using a statistical process or some other process. And the extracted wavelets are then extracted wavelets and the spectra. They are what we are showing here. And prior to the offset to angle domain conversion, the pre-stack seismic data in the form of offset gathers, they were preconditioned by way of background noise removal or suppression and trim static application to enhance the signal to noise ratio. So you can notice that the spectra of the wavelets extracted from the near mid far um, exhibit a lowering in the frequency as we go from the near to far offsets, that is through the middle angle stack. And these effects, you can say they are a manifestation of the offset to angle dependent attenuation as well as changes in the seismic wavelet with time or depth. So now we can compensate this by balancing or flattening the spectrum, that is by spectral balancing, as I have said. So notice after spectral balancing, the equivalent wavelets, they are shown on top and the spectra are shown here. Notice the wavelets are all consistent now as going from near to far, and the spectra are also almost balanced and they are all flat. And so again, before and after, before and after. So pre-stack simultaneous impedance inversion is carried out with these wavelets and the balanced near mid-far angle stacks. They show a higher resolution, and that is going to lead to more accurate interpretation. So I show you here an impedance section before, and this is the impedance section after spectral balancing. So notice before and after. And so, what do we observe here? We'll observe crisper look of the anomalies as well as other events, and they're better stand out on the sections after spectral balancing. So again, before and after spectral balancing. So this definitely adds to the resolution of the data, which we are going to take forward. And one of the things that we adopt while doing these kinds of analysis, especially in quantitative interpretation, they are the use of rock physics templates. And the rock physics templates, they have become over a period of time, I think they were introduced back in 2004. So over a period of time, they have become an effective tool for delineation of lithology and fluid content. And they represent a visual integration of well log and seismic data and their calibration. And that leads to more quantitative interpretation. Now, these templates that I'm showing you here, they are first constructed or modeled from the well log data using theoretical rock physics principles used for generation of trends for different lithologies and fluids that are expected in the area. And once they are generated, they are used as an aid or a guide for interpretation of the elastic inversion derived attributes. Now, softwares have been designed to generate these. Once we feed in the appropriate parameters, then they can be generated easily. And we see here a template overlaid on the cross plot between the P impedance and the P impedance that you see on the x-axis and the VP by VS data plotted along the y-axis for an interval of interest. And the cluster points are color coded with the porosity ranging from 5 to 25%. Now the cluster of points with low impedance and low VP by VS exhibit high porosity, as you can make out, and low impedance and low VP by VS, they are seen here exhibiting high porosity, high gas saturation, and they are enclosed in these red and purple polygons. And now when they are back projected to the well log data, as you see here, they highlight the intervals of our interest. Now, I won't go into the details of the case study here that we had carried out, but more details can be picked up on this reference. I mean, if you can access this on our website also. Um, Now, we had done this exercise, this previous exercise that I just talked about from using well data. A similar cross plot for P impedance and VP by VS ratio derived from pre-stack simultaneous inversion without the frequency balancing is constructed here, and with the overlaid with the RPT is overlaid. Notice the cluster points; they have a shape that is similar to this overall shape of the clusters. They are similar to what we got with the log data. But the drawback we see is that the cluster points within the red and the purple polygons, they are not spread out. They are not populating now in those ellipses very well. So we repeat the exercise after spectral balancing, and notice now on this equivalent cross plot between the two. two parameters. We see a good spread of the cluster points within the red and the purple polygons. And when we back project them, they will highlight the points on the vertical section much better. And that is what we show here, not here, but in the case study that we published in interpretation. So you can pick out all those details. So this is how spectral balancing it helps in our exercises. So before and after, so that is what I was showing there. Now, the next example is from deepwater Taranaki Basin located off the northwest coast of New Zealand. And it has considerable potential for big hydrocarbon discoveries. The seismic, this slide shows a comparison of segments of seismic sections traversing the deepwater channel complex before and after spectral balancing, and their spectra, frequency spectra, they are also shown below. Notice the well-defined appearance of the reflections both inside and outside the inside and outside of the channel complex uh, before and after spectral balancing. And their spectra also, you see a much flatter spectrum on the right hand side. The data volume was then put through structure oriented filtering, and then we generated a number of attributes, including spectral decomposition. And here we see the core-rendered spectral magnitude as a function of, core-rendered RGB core-rendered spectral magnitude that would suffice to say here. And the spectral magnitudes were used at frequencies of 15, 25, and 35 hertz. But after spectral balancing and the flatter spectrum, the frequencies utilized were 25, 35, and 50 hertz. And so you notice RGB rendering, how it brings out the difference. I believe the energy ratio coherence was also utilized to or co-rendered with this display in the background using transparency. And then we made use of the SOM, unsupervised machine learning classification technique. And here we show on the left hand side the SOM cross plot volume from which the time slice at 3.18 millisecond, 3.18 seconds has been extracted. So notice before spectral balancing on the left and after spectral balancing on the right, the image to the left shows the display for the SOM computation when the attributes are computed on the input seismic data, and the image to the right, the equivalent display when the attributes are computed on the frequency balanced data. And these attributes that we use, they were the sweetness, we had used relative acoustic impedance, total energy, reflector convergence, and spectral magnitudes at a couple of frequencies. And those details again you can pick up from the reference that is shown below. So far we have seen examples where we have shown how spectral balancing enhances the frequency content of the seismic data and preserves the amplitudes and leads to more accurate definition of the features of our interest. We will now show that attributes computed from spectrally balanced data better delineate the finer features in the zone of interest. And some attribute combinations can be effectively combined, as I showed in the previous set of slides, for seismic phases classification using unsupervised machine learning techniques. And in this example, we'll see displays from k-means clustering, or shall I say a comparison of displays from k-means clustering, SOM, self-organizing mapping, and generative topographic mapping methods, or GTM method. So we demonstrate these displays or these classifications on a data set from the Smia area in Norway, as is shown on the index map here. The bin size for this data was 12.5 by 25 meters. Sample interval was 4 millisecond, and we have two wells over this 3D volume, 3241 on the left and 3221 on the right hand side, and along with the well data for which we had for these two wells we had the gamma ray, sonic, and density curves, and the quality of the seismic data was reasonably good. So these were some of the things to mention for this particular slide. Here I show a segment of an inline seismic section which is passing through the 3D volume. And I show here data before spectral balancing, and notice the appearance of the reflection of the data after spectral balancing. They will change, and you notice here I have overlaid different markers. You can first notice the well-defined appearance of the reflections after spectral balancing. I'll go back and forth again, and you will notice that. Another thing to point out is that the Sogeny Fjord formation that you see here in green is the primary reservoir consisting of medium to coarse grain, well sorted micaceous and minor argillaceous sandstone. So essentially, it is representing sandstone. And then we have below this Sogeny Fjord formation is the Fens Fjord formation that you see there, and it again consists of medium grained, well sorted sandstone with shale intercalations. And underlying the Fens Fjord is the Cross Fjord formation with medium to coarse grained, well sorted sandstone again. And overlying the Sogeny Fjord formation are the shales of the Heather and the Dropney formations, which serve as primary seals. And so the idea was to use this reservoir for CO2 sequestration. But anyhow, I won't go into that aspect. But the idea here is to show the advantage of spectrally balancing the data and see how it impacts the machine learning application for unsupervised facies classification. And so again, before and after. And so before and after, notice the spectrum on the right hand side, how it becomes flatter after spectral balancing. Different attributes are computed because you are going to use the machine learning techniques for facies classification, unsupervised facies classification. And so the attributes that we computed, they were relative acoustic impedance, instantaneous amplitude, frequency, sweetness, GLCM, which is gray level co-occurrence matrix, energy, computation, and spectral magnitudes at different frequencies. So we are going to look at a segment of a section, or we are looking at a segment of a seismic section from the input seismic data, and this is what we get on the spectrally balanced data. So notice again, input data and spectrally balanced. Input data, spectrally balanced. Now, a stratal slice comparison is shown here, 32 milliseconds above the Sogeny Fjord marker, where we see some of these faults tend to show up nicely. But after spectral balancing, notice the crisp definition of these faults as indicated by the white arrows. And you notice if you compare the highlighted zones, they are far better defined, and that will result in more accurate interpretation of these faults of these lineaments. Now we apply three different unsupervised seismic facies classification machine learning methods to the two attribute data. K-means, self-organizing, SOM and GTM, because I've already mentioned these. Now, due to the paucity of time that I have here, I will not go into the details of the algorithms here, but simply mention that these three methods represent unsupervised classification clustering techniques, which attempt to explicitly cluster the data into a finite number of groups, which in some metric we will say best represents the data. So all the attribute data should first be scaled because they could be in different units of measurements, and so a z-score normalization usually involves a computation of their mean and standard deviation, which is done, and then they are used in these computations. So I show you here a stratal slice at 80 milliseconds below the Sogeny Fjord marker, which is essentially represents the Sogeny Fjord formation or interval, and that is extracted from the k-means volume. Now, keep in mind the number of colors that we see here. There are only two on the upper display, whereas we see more number of colors on the lower display. And also the facies that you see on the left hand side at this well, they could be different from the facies that you see on the right hand side, and that you make out in the lower image as well. So the number 5 that we have chosen is for the number of clusters, essentially represents the number of facies that we expect at this level. And the number given to us was 5. And so that is why 5 is no magic number. This is 136 milliseconds below the Sojny Fjord marker, which is essentially the Fens Fjord formation. And notice here again, we see something very similar. And notice again, this facies is different from this facies. And then within the crossfield formation, we have the same story, same conclusion, and notice the more number of facies. One thing I forgot to mention, that was the lineaments that you see in black. They are from the core-rendered coherence. Now the coherence which is computed, which is shown core-rendered here, was computed on the input seismic data, and here the coherence that is computed, that was on the spectrally balanced data. So notice there is a difference between those two lineaments also. A far better definition in terms of continuity and their focus and all that. And you can make that out here much better. This is the equivalent 80 milliseconds below the Sojny Fjord marker from the SOM cross plot before spectral balancing, after spectral balancing, and notice how much more resolution we are gaining by doing this, or just spectrally balancing the data. This is in the Fens Fjord formation, and notice again, same thing. And then I show you the within the cross fjord uh, formation. Much better definition of the lineaments here, and the overall number of colors of facies. This is stratus slices at 80 milliseconds below the Sojny Fjord, again from the GTM cross plot volume. See, these are different. More number of colors we see here, but they are what you see on the lower image. There is still higher resolution, and the number of and not number, but the faces that we see on the left hand side, they are different from the faces we see on the right hand side. And I'm going to come back to this in a matter of just a couple of more slides. At the Fensfjord formation, again, I show you something very similar. More resolution, more number of faces, and then at the crossfjord, within the crossfjord formation, again the same conclusion that I draw here. Now, to in this comparison that we have drawn for these different facies from the original data and the spectrally balanced one, we almost saw no variation of the facies carried out on the on the data before spectral balancing, and a definite variation of facies on the data after spectral balancing. Now, to just ascertain such a variation, we picked up the the well data from the two wells and carried out a Bayesian facies classification. And so the image to the left here shows a cross plot of porosity that you see on the vertical axis and gamma ray on the x-axis, and the data is from the two wells. Now, the blue one coming from the 4-1 well and the yellow one coming from the 2-1 well. So based on the cutoff values for porosity and gamma ray, the 5 different ellipses they were generated or assigned to the cluster points based on Bayesian classification. So when we back projected them on the vertical curves, we see they highlight zones based on the color of the clusters they represent, and you see those colors of the different clusters, these ellipses. So what we notice is that the red faces in well 4-1 on the left appear as green on the in the well 2-1 on the right hand side, and that is not only in one formation, in one interval. It is Sojny in the Sojny Fjord, in the Fens Fjord, and then the Cross Fjord levels. So this lends support to the facies variation we see after spectral enhancement of the seismic data. So with all this said, now we can turn to some conclusions. And what I state here is that we have found that spectral balancing of the input seismic data, when used for attribute generation and further used in some of the multi-attribute processes that we have discussed, they can significantly help with the accurate interpretation. So next is that the results obtained for the unsupervised machine learning applications employing both the input seismic as well as the spectrally balanced versions depict superior performance of the latter in terms of clarity of clusters as well as color variations within them, and probably in response to the expected geologic variations as mentioned in the introduction. I had briefly alluded to that. Usually, the seismic facies maps in the zone of interest are calibrated with the lithofacies information obtained from well cores and cuttings. Now we are aware that there is, appreciable difference in resolution between the well data or cutting data and the seismic data. So it is, we think it is advisable to enhance the resolution of the seismic data so that we can narrow down the gap between the resolution of the two types of data, that is geologic and seismic data. And finally, I would say, though the analysis that I have talked about here is qualitative at present, it paves the way for more detailed work as more well and other types of data become available. So with this, um, both Ritesh and I would like to acknowledge the ASPI consortium for the excellent research work that is being done here, and also the use of the software. And I would also like to thank Subsurface AI for the use of the software that is geomodeling. Earlier it was called Geomodeling Technology Corporation. Now it's referred to as Subsurface AI. And with these words, finally, I end my presentation and I thank you all for your kind attention. If you have any questions, please let me know and I would be very happy to answer them. So thank you very much.